Hello everyone, in the previous video tutorial we simulated a steady state membrane dialysis process. In this part we shall simulate the transient or time dependent membrane dialysis. This is the transient membrane dialysis process. You can see that the dialysate is passed through the membrane module and this is then returned to a mixing tank and is again fed to the module. So the initial concentration in the tank is 100 mole per meter cube, and we shall do simulation and find out that how the concentration changes with respect to time in this tank. So the dialysate is actually returned to the mixing tank, while it is each time it is brought into contact with the fresh permeate. So we will actually use the reaction engineering module. We will model our mixing tank using the reaction engineering module. We are not going to define any reaction. We will just define a CCR model, continuous integrator model, and that will be just a mixing tank, and we will not define any reactions. So these are the results that we are going to obtain. You can see this is the concentration profile at 0 second, this is a 500 second, and after 1 hour this is the concentration profile. So you can see that the concentration in the membrane in the dialysate side, it falls from 100 to 65, around about 65. And this is another result that we are going to obtain. You can see that the concentration in the tank, this blue is the concentration in the tank, it falls as the time on progress. So go to the COMSOL Multiphysics, and here we will add another physics. Click on the physics, click on the add physics, and here go to the chemical species transport and double click on reaction engineering. Okay, so you can see that this reaction engineering module is added to our process now. Just right click on this reaction engineering module and click on species, and let's suppose we name the species as species A. Click apply, and in the reaction engineering module select the reactor type as a CSTR constant volume. Okay, and the volume of the CSTR is 1 exponential minus 3 meter cube. Now right click on the reaction engineering module and click on the feed inlet. Here you have to define the volumetric flow rate, volumetric feed flow rate, which is entering into the reactor, and this is the initial concentration, the feed initial concentration. So the volumetric feed flow rate is I will just write this expression here. This component 1 means this is the component 1 that we are working in component 1, and SPP is actually, this is the single a single phase flow, and out 1. Which one is out 1? So this SPP out 1, this is actually out 1, this one, right? And volumetric flow rate, so it will calculate the volumetric flow rate at this outlet of the module, and this expression is then used to do the calculation for the volumetric flow rate, which is actually entering into the CSTR. Similarly, I have written this expression here, component 1, TDS, this is a transport of diluted species, out 1, this out 1, this one, right? C naught and average C. This means that input concentration to the reactor will be the average concentration that leaving the module. Okay, now you have to change this inflow 1 in the transport of dialysis species. Here we have to actually enter an expression, and just write this expression here, component 1 RE, this is RE, right? RE and CA. What does it mean? RE is for the reaction engineering module, and CA is actually the concentration in this CSTR, right? So that means that the input concentration will be the one that is leaving the tank, right? This one, this concentration, which is leaving the reactor, it is entering into the rest module. So this expression is written for that concentration. Now we have to add another study. So just click on the study, click on the add study, and add empty study. Okay, and now add the study steps. So just click on the study, enter a stationary study, and then enter a time dependent study. Okay, you need to enter the stationary study first one, because first it will calculate the outlet concentration at the outlet volumetric rate using the stationary study, and then that will be used in the time dependent study. So click on the time dependent study, and here click on this range 0, 1, and 3600. That means that it will do simulation for the process up to 3600 seconds with an interval of 1 second. Okay, now click on add. Sorry, you need to replace this. Okay, so 0, it will start from 0 with 1 second step time, and up to 3600 seconds. Okay, there something that I forgot. That is the initial value, because we didn't enter the initial value in the tank. So for that, go to the reaction engineering module, click on the initial values, and this initial value is C1N. C1 in this, which is a 100 mole per meter cube. We have already found that in our parameter section. Okay, now go to the study, and just click on the compute button. So this is the concentration file. You can see it here. I will just remove the streamline, delete this streamline. Okay, and this concentration, let's me call this concentration study 2. Okay, now this is the concentration profile at 3600 seconds. Sorry, this is concentration profile at 0 second, right? So if you just click on this arrow, so this is the concentration profile after 1 hour. So initially you can see that the concentration is 100 mole per meter cube. If you just check this profile at 3600 seconds, so you can see this falls to 60 seconds. Okay, you can right click on surface and click on selection in the same way, and just duplicate this, and this selection one, click on this button and deselect the first domain, select the second one, again the duplicate. Okay, so selection, deselect this, select this one, another duplicate, and click on selection and select this one. Okay, now you can see the concentration profile in all of the 4 section, and these are the scales. This one for the dialysis side, this one for the first membrane, and so on. So initially it was like this. Okay, and after 3600 concentration, 3600 seconds, the concentration falls to 65 mole per meter cube. If you want to check this at any time, so any other time, so let's suppose I want to check this after 406 seconds, click on plot. So this is the concentration profile after 406 seconds. Okay, you can also plot the 1D concentration profile. So click on the results, click on the 1D plot graph, and click on the line graph. Okay, and Click on the study 2 solution 2 and select this outlet boundaries and time selection. Let's suppose this I want to see at 0 second, at 500 second, at 1000 second, 1500 second, 2500 second, 3000 seconds, and 3600 seconds. Okay, and click on plot. You can display the legend from here. So this is the concentration profile at different time zone. This is the concentration profile at 0 second, and this is the concentration profile after 3600 seconds. Uh, so now I want to see the concentration in the tank, that how the concentration changes with respect to time in the tank. So for that, click on the results, click on the 1D plot graph, right click and then add global. Okay, so I'm just writing this expression here. This means the component 1 transport of dilute species out 1 dot C naught every C. So this is actually out 1 is the outlet of the dialysate. So this means the concentration, the average concentration at the outlet of the dialysate, right? And of course this is from the study 2. So if you just click on plot, so this is the concentration at the outlet of the this is the concentration at the outlet of the module with respect to time, and you can see that the concentration falls as the time progresses. We also want to see the concentration in the tank with respect to time. So for that, add another global and write this expression here, re dot c underscore a. Re means this reaction engineering module which we have added to our studies, this RE, and CA is the concentration in the tank which we have already defined with the this, we have defined this species A. So enter mole per meter cube here, this is the unit, and now click on plot. Sorry, there is some problem with this. Let me check global 2 and just select study 2, enter mole per meter cube, sorry, mole per meter cube, click on plot. So this is the concentration. This one is the concentration in the tank with respect to time. Okay, you can actually enter legends from here. So just write manual. So concentration in tank, and this legend is now appeared here, and you can also change this one as well. So automatic, and this is manual. So just write the concentration at okay, outlet concentration of dialysate, and click on plot. So the blue line is the concentration at the outlet of dialysate, and the green one is the concentration in the tank. And you can see that as the time progress, the concentration falls. So this was all about the steady state and time dependent membrane dialysis. If you have any question, please put that in the comment section, and please subscribe to this channel. And if you want to simulate some specific process, so put your recommendation in the comment section, and I will try to upload a video on those recommended problem. Thank you very much.